Hi, my name is Yuganeswarman. My metric number is 143470, and today I will talk about the applications of liquid crystal. So before we go into talking about the application of liquid crystal, let's just see what liquid crystals are. So liquid crystals are a unique state of matter that is between solid and also liquid phase. So here in this picture we can see the liquid and also the solid and also the liquid phases, as well as what's in the middle, which is the liquid crystal. So here for solid we see that the matters are in an orderly manner, but for liquid it's everywhere, it's randomly arranged. But for liquid we know that it can be moved around at anywhere. So for liquid it possesses both of these properties, which means liquid crystal have somewhat of an orderly mannered matter, but at the same time it can be this each individual matters can be moved around easily, just like in liquid. So liquid crystal materials generally have several common characteristics, such as rod-like molecular structure, like this, a rigidness of the long axis, which goes in this direction, and also strong dipoles, which can be easily manipulated using electric and also magnetic fields. So now let's look into the first application of liquid crystal, which is the liquid crystal or LC thermometer. So an LC thermometer is just a self-adhesive label consisting of a series of temperature-sensitive elements that contains something called micro-encapsulated thermochromic liquid crystal, TLC, which is coated on a black backing. So this TLC will be very important in discussing how the mechanism, how this thermometer works. Alright, so on my left we have a thermometer. So how does this thermometer work? Let's look into it. So the temperature-sensitive element contains TLC molecule that are very sensitive to temperature. So the change of position will happen, or the twist will happen in relation to change in temperature. So what kind of twist are we talking about here? So this change in molecular structure affects the wavelength of light. So basically the twist will happen in the molecular structure of the liquid crystal. So this will then affect the wavelength of light that is absorbed and reflected by the liquid crystal. So this will result in an apparent change of the color of each temperature event, meaning when there is a different temperature that is subjected to the liquid crystal here, what happens is that the molecular structure changes, and these changes will affect the wavelength that is absorbed. So let's look at the 20 degrees Celsius here. When the rated temperature of an indicator is reached, the TLC molecule twists slightly, causing the TLC substance to absorb the red and blue portion and reflect the green part only. So that's what's happening here. So this causes the temperature event to appear green. When the temperature decreases, the molecule begins to twist and in the opposite direction. So this is going backwards, and the TLC reflects a different portion of the spectrum, which means over here the blue color at 18 degrees Celsius. So that is how the liquid crystal thermometer works. So now let's see the second application, which is the liquid crystal lasers. A liquid crystal laser is a laser that uses a liquid crystal as the resonator cavity, allowing selection of emission wavelength and polarization from the active laser medium. So this liquid crystal laser basically allows us to choose our own wavelength that we want. How does it work? Let's look at the mechanism. So starting from the liquid crystal in the nematic phase, we try to achieve the desired helical pitch by doping the liquid crystal with a chiral molecule. So this is the outcome, which is called liquid crystal helical structure. Now this is done by doping the liquid crystal with a chiral molecule. So the reason why we do this is because we want to get a desired helical pitch. Now the reason why we want a desired helical pitch is because we want to be able to produce a helical pitch that only reflects a certain wavelength of light. So let's say in our case we want to reflect the light red. So basically this helical pitch will only reflect the light selectively, that is the red wavelength, that is from the red wavelength. So what really happens is that when the structure is optically excited, it will start to emit the red color light, because once it is optically excited, light goes in and only the red wavelength will be emitted out. So that's how this liquid crystal laser works. So where is it applied? Usually it is applied in telecommunication devices such as TV, computers, mobile phones, etc. The lasers are small enough to act as individual picture elements of a display. Next, it is also incorporated into fiber optics, and this will open up applications in dermatology, cancer, and also diabetes detection. So let's now talk about our last application, which is liquid crystal lenses. So these liquid crystal contact lenses have variable focus. These switchable contact lenses varies its refractive index with changing applied voltage. So with changing applied voltage, we have changing refractive index. So let's look at how it works. The molecules that form nematic liquid crystals are usually rod-like. So these are the rod-like nematic liquid crystals that we see here. Nematic liquid crystals' physical properties such as its refractive index varies depending on the local value of the director. This basically just means that this rod-like structure has varied refractive index based on the director. So the director is how the rod-shaped molecules move. So maybe here we have a different refractive index, and maybe here we have another different refractive index based on how these molecules move about. So how can we take advantage of this? We can apply a voltage above a particular value that will orient the director either parallel or perpendicular to the electric field's direction. Alright, so when we apply the voltage, we can change the director and we can change the refractive index. So let's look more into the anatomy and also the mechanism of this lens. So at first, we can see that the substrate PMMA, which is mostly used in contact lenses, sandwiches the liquid crystal in between. So on top we have the same PMMA substrate, on bottom also we have same PMMA substrate. This is where the eye will go about. And in the middle is what we are really concerned about, which is a liquid crystal. But we also have something called indium tin oxide, ITO electrode, which is where the electricity will be passed through to change the director inside the liquid crystal, so we can change the refractive index, which will also affect the focal power of the lens. So this is how it works. We pass through some electricity, which will apply some voltage into the liquid crystal that will change the director and will change the refractive index, which will also change the focal power of the lens. So that is it for anatomy and mechanism of this lens. And thank you for listening.